from your normal day-to-day life in genes. You can apply the principles of thermodynamics. You can apply it anywhere and try to model it. Try to study this. So, starting with studying the system. So, what does the system mean?
We'll wait a couple more minutes and we'll start at 6. So, welcome to Thermodynamics problem solving session. It's the first week. So, uh, we'll start with understanding thermodynamics. I'll just brief you about uh, what has been covered mostly in the lectures. We'll see a brief overview of those and then proceed to see some problems. And you can if you have any doubts, you can ask anyway in between. So to start with, what is thermodynamics and why is it useful? So thermodynamics is you can see thermo energy or heat, dynamics in motion. So what we are doing is we are trying to analyze how an energy is being transferred or modified, or analyze the system basically. It all started with converting or producing work with analyzing engines and so on. So the field evolved. So and whatever what you will see, the state, the laws which are say are all, you don't have any proofs for that, but mostly are developed over years based on observation and facts. So that's why you will not find any proofs of the thermodynamic laws stated, like the zeroth law, or what you will see hide in first law or second law. So as I said, you start with, to take an example for an engine. So you want to analyze the system. So thermodynamics is like a tool for you. You apply it anywhere. Can whatever you see around, you can put it with thermodynamics. You try to analyze it. This heat and work transfer or an energy in any form, how it is getting coming in or going out, or how it is getting converted. This thermodynamics will be useful in understanding or analyzing or building systems for which are more efficient or on this aspects. So learning thermodynamics helps you there. So to start with, we need to know certain terminologies which are used in thermodynamics. So these are, I've listed it out. So starting with is a system. So system in general is whatever you want to study or whatever your focus is on. So that you call it a system. So again, the system can be classified into different types, so which we'll look at again. But here I've given a shape or volume of a system being analyzed. This cannot be, so you can say it is not like a constant. It can be varying. Like if you are saying you are you have a balloon, and the balloon is you are filling in air, so it's expanding. So here the balloon itself can be your system. So it's not rigid, or it's not a fixed shape, but it can vary. So it depends again on the type of system. So next is surrounding. So what do you call this surrounding? So surrounding is anything but the system. Anything outside of the system, that you call it surrounding. So environment, so your whole universe except what you are studying, it becomes your surrounding. Then boundary is the one which separates these two. The one which you are considering as a system and you are trying to analyze, and which is separating this from the environment, is you call this the boundary. And anything this crossing this boundary is what we'll be looking at as a energy in motion. So heat or work which is transferring this boundary, that will be only be our focus we're seeing. So coming back to the system, so this system can be of types. So one is a closed system, by which you call there is no transfer of mass. So you can have energy transfer, but you cannot have a mass transfer. So that you call as closed system or controlled mass system. In some term, some books, or they call it controlled mass. And then you have an isolated system. So isolated system, you have there is no mass transfer, you don't have any energy transfer, so it doesn't interact in any way with the surrounding, so it is totally isolated. So in that case, you call it as an isolated system. So previously closed system, you didn't have any energy transfer, so sorry, you didn't have any mass transfer, so that's why it's called controlled mass or closed system. Then isolated system, you don't have any mass as well as energy, then it's an isolated. Then you have a controlled volume. In this case, you have a fixed system. This is called as an open system as well, or control volume. In this case, you have both mass and energy which is transfer which is happening across the boundary. Then you come across something called as property. So what is property? The property is a characteristic of system. Like every person has a name, so to define. So like that system has some characteristics to define it. So that is a property, and it can be of examples: mass, volume, energy, pressure, and temperature. So which any property, if you see any system or state can be defined using these properties. So a state refers to condition of the system. So uh, suppose to give an example, I am at first floor or something. So my name, suppose you consider as a property, so which is defined myself, and the way where I am resting or how you describe the system. So that is the state. So the changes of this states comprises of a process. How your system undergoes the changes in state, that is called termed as a process. So these are all terminologies which we'll be using often in the course. So again, this property can be of two types. So one is called as an extensive property, and the second is called as an intensive property. So how do you differentiate between these two? So what is an extensive and what is intensive? So intensive is independent of mass, you can say, and extensive is dependent of mass. So okay, by definition this is how, but how exactly will you differentiate? So for example, if you say you take 2 kgs of water, for example, and you split it into two parts. If you see, your masses in each of it would have changed. So each part will have a different mass. So if you split it equally, you will have a kg and kg. But you know the density of water, so 1000 if you take, so both will have equal densities. So this density is irrespective of splitting it into multiple parts or smaller parts, the density of that will remain same. So that is an intensive property. Similarly, if you take a boiling water, you assume that whole water is of uniform temperature, you try to split it again, the equal parts or the smaller parts, whatever you are splitting it, the temperature of each of the parts will remain same, so it will not vary. So again, that will be an intensive property. So that's the case. Again, if you see pressure, the whole, you assume the whole atmosphere, you have atmospheric pressure. It will not be any different unless some process or something is happening. Yeah. Okay. So again, that will become an intensive property. So extensive properties are those which uh, have a dependency on mass, and intensive is in which is independent of mass. So it's a simple match problem. You can try to match this, and I'll be answering this again. You can try what we have just gone through all of it. You try to match it. I'll give you a minute. I hope the terminologies are clear. If you have any doubts, you can ask. So I'll solve. So first, I'll just answer it based on A, B, C, D. So A, the condition of the system as described by its property is state. So 8 is a region of space through which mass may flow. So there is a mass transfer. So only can happen is during control volume. So that is a region of space. You have focus on a fixed space. So you put a or define a boundary of a fixed space or a fixed area, or volume, whatever you define. So that is your fixed focus of the system. So there it is a control volume. So you are controlling the volume. So that's why control volume. So whatever is studied, so that is your system. So D, a transformation from one state to another. So that is a process. E, a property whose value for an overall system is the sum of its property for the parts into which the system is divided. For an overall system is the sum of its. So E is an extensive property. So everything external to the system is your surroundings. A fixed quantity of matter is a controlled system or a closed system. A property whose value is independent of the size or extent of a system and may vary from place to place within the system in any moment. So independent of size or extent, independent of mass. So it's intensive property. So it distinguishes the system from its surrounding, that is your boundary, and a macroscopic characteristic of a system to which a numerical value can be assigned at a given time without knowledge of the previous behavior of the, that is your property. So I hope everyone got it right. So few examples we'll see of types of systems. So here we have an example. So insulated fixed volume, a closed insulated fixed volume. So here is an isolated system. So there is no heat transfer, there is no or energy transfer, there is no mass transfer. So this, if you see an example, this is your thermos flask, for example. So there ideally a thermos flask where you don't lose any heat, or whatever the contents inside stays hot. So in that case there is no heat transfer, and since it is a closed, you don't have any mass transfer as well. So that's your kind of an isolated system. Another example is a whole universe where there is nothing going out or coming in, there is no transfer. So that is your isolated system. Second is closed but non-adiabatic and without work. So non-adiabatic, so there is heat transfer here. So in that case you have a system, you have some mass inside, but there is no mass transfer, but there is a heat transfer. So this is your controlled mass or a closed system. So again, so if you take the same thermos flask example, you have the insulation is bad in this case. So in that case you have heat transfer. So now it becomes as a closed system. So closed adiabatic with work. So this could be another example. So here instead of heat transfer, you have work transfer. So this again still is a closed system, but instead of heat transfer, you have work transfer. So any kind of energy transfer, but there is no mass transfer. This is a closed system. So this line is a piston cylinder arrangement. So which you see in engines and so on. So with an insulation, we will have only work, but there is no heat transfer. So there will be still a control system. Sorry, control mass or closed system. So having both heat and work transfer. So again it says closed system. So there is no mass transfer. Then you have a pipe which is insulated. So there is no heat transfer, but fluid is flowing inside. So this is an open system. Example of an open system. So open system, not necessarily that you need to have both mass and energy transfer. You can have either of it. So open system, here you don't have any sorry, open system, you need to have mass transfer, but the energy transfer as a heat. Here you will see there this will have some work transfer in later part of the course. So you have a tube where you have some contents flowing. So if you consider this whole part as your system, which is your space of study, so there is some amount of mass which is coming in and some amount of mass which is leaving out. So you are constraining to a particular volume, or your focus is a fixed volume. So this will be a control volume or an open system. Similarly, you have two tubes. This is like an heat exchanger. So you have two tubes where there is a heat transfer between these tubes, and there are mass transfer which is happening. So if you assume the whole system again here, so you have mass transfers which is going outside the boundaries. So this is again an open system. So the example is an heat exchanger. So again similarly you ought to see pumps, reciprocating pumps, or a piston compressor in the engine. So all can be brought down as a system, and the mass transfer and energy transfer can be accounted, and you can see how the system can be break into pieces and can be brought into study. So reciprocating pump, again you have a piston cylinder arrangement, so you have work and mass transfer. So it's again an open system, and similarly piston. So again these are turbines and compressors. So these are all system components which you will come across in thermodynamics. So how again the system can vary based on how the system is perceived. So as I told previously, you have a balloon which you are inflating. If you assume the balloon is your system, so it will become a control volume open. But if you assume the mass which is there inside the balloon, so you have a balloon filled with air, you puncture it. So the air inside, if you consider that then it becomes a control mass. But if you assume that balloon boundary is your system, then that will becomes a control volume. So again a similar example, you have a teacup, whatever you have content is hot. So in this case there will be some evaporation happening through the mass transfer and heat transfer. So this is an open system. Again if you close it, so now you are not allowing any mass to go out. So but you have heat transfer. So this how you're putting it, and then you have thermostats which don't have any, so it becomes an isolated. So here I have listed some examples on the intensive properties. So we have to find out which is the list containing only the intensive properties. So first one, A is volume, temperature and pressure. B is specific volume, mass, volume, and C is pressure, temperature, specific volume. D is mass, temperature and pressure. Yes, so the answer is option C, pressure, temperature and specific volume. A specific volume is your inverse of density, so volume by mass, so that you are dividing by mass and making it independent. So volume, as I said, you have a bigger, if you say 2 liters of water, same example. So if you split it into smaller volumes, your mass of that will also change. So not necessarily the specific volume. So mass again is an intensive property. So we have seen pressure and temperatures are intensive property. So option C here is the right option. Pressure, temperature and specific volume. So the next is a simple example to find out the specific volume or density. So how do you do that? So 1 meter cube container shown here as filled with 0.12 meter cube of granite, 0.15 meter cube of sand, and 0.2 meter cube of liquid at 25 degrees Celsius. So the rest of the volume is 0.53 meter cube of air with a density of 1.15 kg per meter cube. So we need to find out the overall specific volume and density. So, and density of each of the components is given: granite, sand, water, and air. So how will you find the overall? So simplest is to find the total mass, and you know that volume, and you can find out the specific volume or density. So we'll first find out the mass of granite. So specific volume is volume by mass, and specific density is mass by volume. So mass of granite is your density of granite into volume of granite, so which is given. So similarly for other sand, water, and air. So density of granite is 2750 kg per meter cube into 0.12 meter cube. So we get 330 kg. And similarly for sand we get 225 kg, and water 199.4 kg, and air is 0.61. So the total specific volume will be, overall specific volume will be the total volume divided by the total mass. So total volume is 1 meter cube. So it comes out to be 0.001325 meter cube per kg, and density is 755 kg per meter cube. So in the problem it said to find the overall density, and air was given. So if we would need to find out just the mixture, you would have to exclude air. So the next question is
Sir, please go to the back question, sir. Once.
yeah. Any doubt in this
Question.
question? Okay.
Okay, sir.
Okay. So the problem on to find out the pressures and the height and so on, in terms of measuring and pressure. So it's all we are looking at this to see because any system there are properties which can be measured and which cannot be measured. So pressure, temperatures are properties which are measurable properties. So you use some kind of measurements tools to measure this property. So you will come across some other properties while in the coming weeks, so which cannot be actually measured. So these properties are represented in terms of property which can be measured. So we are looking at some of the examples to find these measurable properties, and now problems relating to those. So pressure is one such property which you can be measured, and it is used across various streams. Let it be in hospitals, you find out blood pressures. So there use in terms of mercury columns, and now mostly being digital. Previously you would have seen they have a column and they have a balloon kind of thing which they keep on pressurizing to see the pressures. So it's a form of pressure measurement. And similarly your atmospheric pressures which been monitored, data is being collected, temperatures and so on. If you open your apps, weathers, you will see the pressures, temperatures and so on. So these are properties which are measured in various fields and being studied. So here's an example on pressure. So barometric pressure at the base of a building is 100.7 kilopascal, and on the roof it is 97.36 kilopascal. So you have a building. So what you have measured the pressure at the bottom of the building, that it comes out to be 100.7 kilopascal, and when you go to the roof, you find that the pressure is 97.36 kilopascal. So we are saying that if the density of air is 1.18 kg per meter cube, so what is the height of the building? So you would have uh, you know that pressure is written as density into g is acceleration due to gravity into height of the fluid or uh, which is you're measuring. So at the top you have some pressure. So when you go down in the fluid or you have rho gh, the density of fluid, g is acceleration 9.81 into your height. So similarly the same concept applies here. You have a building, so you know the two pressures difference. So the pressure difference is rho gh. So that's what I have did. So your pressure is 100.7 at one point and minus 97.36 to find out the difference in pressure, and multiply by 1000 because it is in kilopascal. So I made it into pascal. So pascal is nothing but Newton per meter square. So divide by your rho into g. So rho 1.18 and g 9.807. So from using this we get the height of the building because that's where the two pressures have been measured. So that comes out to be 289 meter. Okay. So a similar problem on pressures, we'll see. So what is the pressure at the bottom of the 7.5 meter tall storage tank of fluid at 25 degrees Celsius as shown in figure? So it's figure it's given. So we have some pressure vessel. So at 25 degrees Celsius we have a storage tank of 7.5 meter tall. Assume that the fluid is gasoline with atmospheric pressure 101 kilopascal on the top surface. So repeat the question for the liquid refrigerant R134A when the top surface pressure is 1 megapascal. So G is given as 9.807 meter per second square, and the densities are given. Rho gasoline is 750 kg per meter cube, and for R134A is a fluid refrigerant. So it is 1206 kg per meter cube. So how do you define this system? So first one is your pressure difference due to gravity. So same problem. As better as you try solving this, we'll see the solution. I'll give you a couple of minutes. Uh, 1 megapascal is 1000 kilopascals. So we'll see the first one for gasoline. So what they have asked is to find out the pressure at the bottom. So pressure is your top pressure plus your pressure difference, which is given by rho gh, your density into multiplied by gravity, acceleration due to gravity, and the height. So here we assume that the whole storage vessel has been filled with gasoline. So from top to bottom, so your pressure difference is rho gh. So your pressure is the top pressure plus your pressure difference. So your rho gh is 750 kg per meter cube into 9.807 meter per second square into 7.5 meter. So this will come out to be 55,164 Pascal, or if you write in terms of kilopascal, it's 55.164 kilopascal. So just dividing by 1000. So now we need to find out the total pressure at the bottom. So that is your atmospheric pressure, which is 101, which is acting at the top, plus your pressure difference. So it comes out to be 55.164. So we'll get 156.2 kilopascal. So that is the pressure at the bottom when it is filled with gasoline. So the same approach for R134A, just that your density is changing here. So the density is 1206 kg per meter cube. So it comes out to be 88704 Pascal. And your pressure, they say that the top surface pressure is 1 megapascal. So 1 megapascal is 1000 kilopascals. So 1000 plus 88.704. So it will close to 1089 kilopascals. Again, here it was 25 degrees Celsius. So there is no heat transfer. So you can assume there is no heat transfer, there is no mass system. You can assume it to be an isolated system or a controlled mass system. In the second, you have minus 160, so there will be heat transfer. Now it becomes a controlled system, and if this is at temperature, you need to have an insulation, so that becomes an isolated system. Okay, so similar problem here. We need to find out what the pressure of the water should be to lift your piston. So, your piston cylinder arrangement, they have said that the cross sectional area is 0.01 meter square and a piston mass of 100 kg. So, you have a piston here, and that is of 100 kgs, and your cross sectional area of this piston is 0.01 meter square. So, it is resting at the top. So, and you have an outside atmospheric pressure which is acting on this piston. So that is of 100 kilopascal. So what should be the water pressure be to lift the piston? So that's the question. So what do you think the pressure of the water should be? So again a simple problem. So just like previous, you have two terms. So two kinds of pressure which is acting on the water. So one is the atmospheric pressure, it is acting on the piston and it is carried over to the water. And second is the pressure exerted by the piston weight. So those are the two kinds of pressure which is acting on the water. So to lift this piston, you need a pressure greater than these two pressures. So that's the answer. So first you need to find out the total amount of pressure which is acting on the water. So first is your 100 kilopascal. So that is given, which is atmospheric pressure which is acting. And second is your weight of the piston. So you have 100 kgs of weight. So the force which will be exerted on the water is 100 into g divided by your area. So that will be the pressure. So that's what your force is P into A, or P is mg, your weight, plus your atmospheric force because of the atmospheric pressure. So P naught into A. So if you are rearranging it, the total pressure which is required is your mg by A, which is the pressure exerted by the piston weight plus your atmospheric pressure. So substituting, you will get, so mass is 100 given, g is 9.81 or 807, divided by area is given 0.001 0.01 meter square, and this 100 kilopascal, sorry, this 100 kg. So dividing by 1000 to make it kilopascal. So I think I have added one more zero here, so I have to remove that. So finally what you will get is 100 plus 98.07, which is 198.07 kilopascal. So we see if you remove atmospheric pressure, so it's like close to 1 bar. You see this is close to 2 bar. So if you remove atmospheric pressure, the pressure which is required is an additional 1 bar. Normal atmospheric pressure is 100 kilopascal, that is 1 bar. So if you see that 1 bar as a pressure can lift 100 kgs. So that's how a single bar of pressure can account to. To give a small note on that. And what do you think will happen if you change water to air? Do you think that the pressure required to lift this piston will be any different? Do you think the force which you have to apply to lift this piston will vary if I replace water with air, a compressed air? Yes? Sorry, I didn't get you.
No, because we are not. I mean, here we are. It is not density. Uh, we are not using density in the equation, so it doesn't matter whether we use water or compressed air.
Okay, yeah, correct. But I think better to see it from a physics point of view. Pressure, whatever, irrespective of fluid, your pressure is same. So whatever the piston is, irrespective of what is there, what is putting pressure on the piston, so it is subjected to the same pressure. Let it be water or some other fluid. So the piston is subject to the same pressure. So it should not matter what is there inside. So your pressure will remain same. It will be irrespective of fluid. So next question: a wind turbine electric generator is mounted atop of tower. As wind blows steadily across the turbine blades, electricity is generated. So the electrical out, A, considering only the wind turbine electric generator as a system, identify locations on the system boundary where the system interacts with the surrounding. Describe changes occurring within the system with time. Put off the generator is fed to a battery. So I'll break it down. So we have a wind turbine electric generator. So just those are the windmills which you see. So that is mounted, and because of the wind which is blowing across the turbine blades, you are generating electricity, and the electricity is coming out is fed into a battery. So that's how the system is looking. So what they are saying here, so considering only the wind turbine and electrical generator as a system, so if you're considering the windmills, those and which is mounted with the electric generator, if that is when considered as a system, so identify location on the system boundary where the system interacts with surrounding. So we need to find the boundary where there is interaction between the system and the surrounding, which is the rest of it. So describe changes occurring with respect to time. So how these are changing. If this generator which is there is putting whatever electricity is there to the battery. So second is repeat the process for the whole considering the windmill, generator and the battery as a system. So that's the two cases. So this is your case. So first you have a windmill. So there wind is blowing, and you have generator which is mounted with the windmill part, and that is connected to the storage battery. So in the first case, this alone becomes your system. So now this is a control volume. So because air is coming in and going out, and that is doing some work on the blades, turbine blades. So your interaction here is with respect to air which is flowing across the boundary. So there is one interaction with the boundary, and second is whatever electricity which is generated, that is going out through the electrical wires. So that is your second interaction which is occurring through the boundary. So if your airflow is steady, so there is no variation, so it will reach a steady state where you get a constant or steady amount of electricity which is coming. So that's what I have. So second case is when you have battery as well as a system. So here what happens is you have the same air which is coming in, so that's one interaction, and second is the whatever energy current is coming in, it is stored in the battery. So now the battery is not a separate system. Okay, only the battery. The second is only the battery, not this. So here the interaction is again your electric current which is coming through the wires. So that is one interaction, and second is normally if you see if you take your phones, you put it on a charge. So what you or when you use it excessively, what you can see is your phone getting heated up. So that is happening because of the electricity which is coming out or coming out of the battery. So the that causes the battery to be heated up. So it the temperature, there is an increase in temperature, so there will be heat transfer. So that is the second part. So there is you have thermal interaction. So that's what I've been written as the battery is charged and chemical reaction occurs within it. So the temperature of battery varies, and that causes a thermal interaction. So those are the two types of interaction which is there. So here if you see your with respect to time, the state of the battery changes because you are initially at no charge and you are fully charging, so on. So the state at each of the point, it's varying with respect to time. So this is not a steady state. So similarly, next question. So the driver of a car of total mass m driving at the speed c must slow down to stop over a given distance L. So the car is driven down a hill with a slope corresponding to an angle alpha. So the internal energy of the car, so the energy of the car, you can say, at rest after cooling is the same as the initial state. So the air drag is neglected. There is no slip of the wheels on the road. So you have braking distance is given as 100 meters. So slope of the hill is given as tan alpha is 0.07. So speed of the car initially is 72 kilometers per hour. So the mass of the car is 1000 kgs and G is given. So calculate the change in the car's energy and calculate the heat generated. So you would have seen your normal physics class, the work energy. So we'll be using the same thing to just to understand how these are happening. So that initially at the top you have the car which is trying to come down at some certain speed, and you're applying brakes, and this brings it to an halt. So and you let it cool to come to your ambient temperature. So what they are saying is how this energy change is happening and what is heat generated. So what you have is your work is heat you have potential energy and kinetic energy. So those are your work and energy transfer. So the work or what you are doing here is to stop the car. So whatever energy is there, that has to be brought to zero, or you're converted back to some other by applying brakes. So initially what you have is some potential energy and some kinetic energy. So you have mv square by 2, which is the kinetic energy, and mgh, which is the potential energy, and you're bringing it to 0. For doing this you require some work. So this is your simple physics work energy interaction which you do, energy balancing. So V we know, which is coming at 70 kilometers per hour, so will be 20 meters per second, and we know H is L sin theta, sin alpha. So we can find out H. So from there we can find out the work done to apply brakes. So that is 1000 into mass is 1000, so 1000 into 20 square by 2 plus your G into your H, 100 sin alpha. This comes out to be 268.7 kilojoule minus. So what happens here is they asked to find out the heat which is generated during braking. So whatever energy work you are applying to bring down the energy, so where will it go? It has to go somewhere. It has to get converted to something. So you have initially a higher amount of energy and you have brought it to 0. So it has to get converted to something else. You don't see anything. So in this case what happens is everything gets converted to heat and dissipated to atmosphere. So whatever work which you are doing gets transferred to heat. So Q is 268.7 kilojoule in this case. Any question in this? So what we applied is a simple your physics class work energy balance, and then we found out work, and then with that the heat. So again going back to system. So this is an example which I have taken to show how you have a bigger power plant or some kind of thing, or whole process industry, whatever you take, how you can apply thermodynamics for a whole plant or a small component. So that's the idea of taking this example. So you have here several components of a power plant. Initially you have you're putting in coal and oil and you're burning it. With that you're generating steam and running a turbine, which again generates electricity, and it is transferred to power grid, and then whatever which is coming out of the turbine, so that will be still hot, so that you are sending it to heat exchanger, to use it as a district heating. So where your cold climates people use heaters or heating, so there you have district heating where you whole district you have a centralized heating arrangement. So for that you use, and then which is goes into loop, and then whatever you are burning, so you have some gas which is coming out, so there you have separating that solid particles in the flue gases, and then you purifying gas and letting out in the chimney. So this whole power plant which you are putting, so if you assume this whole power plant as a your system, so how will you apply the energies? So what is coming in and what is going out? So what flows of mass and energy are in or out, or any storage of energy is there? So that's the question. So how do you solve this? So I now, this is my system, I know. So I don't whole power plant is my system. So I don't care what is there inside. So this is a black box for me. So I am now only interested in what is crossing the boundary, or what is coming in and what is going out. So if you see this whole thing is my power plant black box. So we have coal which is coming in, which will be burnt, and burning those will generate flue gases which is going out, and then for burning these flue gases I will require some air, so that air which is coming in. So these are the mass transfer, and then for district heating which was mentioned, so though the fluid which is coming to get heated up, so those hot water and cold water which is coming in and going out, so those are the mass transfer which is happening, and this is a power plant, so it will generate electricity. So the electrical work or electricity is what which is going out, so that is your energy transfer. So if you see the whole of system, you can put it as control mass and can apply the same energy balances and mass balances. You can do it for a single component, or you can do it for the whole plant as well. So next question, again a pressure measuring problem, so slightly a notch up compared to the previous one. So there are two pipes in a system connected by a W tube manometers as shown in figure, where the brine pipe is connected to a tank filled with different fluids. Oil and brine are flowing in parallel horizontal pipes. So the pressure at the center of the oil pipe is 200 kilopascal. Take the density of water is 1000 kg per meter cube. So we need to find out, write the pressure balance equation between points 1 and 2. So 1 is where the oil is center of the oil pipe, and 2 is the brine, center at the brine. And then find the pressure at point 2. And similarly, we have to write the pressure balance between 2 and 3 and find the pressure at 3. So whatever fluids are there and their specific gravity is given. So specific gravity is nothing but your rho of fluid divided by rho of water. So see, that's why specific gravity of water is 1. So you can assume density of water as 1000 kg per meter cube. So using that you can find out rest of the densities. So try solving this. I'll give you some 2-3 minutes or more. See. solved attempted this problem. So we'll see how to solve this. So first is your pressure balance between these 2 points 1 and 2. So how will you do that? So pressure at 1, so P1 water pressure, plus you have some pressure till the oil column is there, or where the mercury is starting. So that is given as 50 centimeter. So rho of oil into G into H. So that is what is the pressure reacting at this point here, where the mercury is starting. Right. Can I put a pointer? Okay, anyway, so oil, so whatever the oil column is there 50 centimeter, so till there, so rho of oil into G into H, and then at this point mercury, both will be at same pressure. So the mercury at the side, so if you come from the other side, so what we'll have is so P1, which I have written P1 plus rho of oil into G into 0.5, if you are writing in terms of meters. So this pressure will be equal to the other side, if you write it from the other side. So you get P2 plus rho of your brine into G into H, which is 50 centimeter. Sorry, if you write minus, so bottom will be plus, top will be minus. Then this air here at the start of brine will be equal to the same height in the left side. So minus, you will have a rho of air into G into 0.6 minus rho of mercury into G into 0.1. So you have to rearrange, you will get this equation here. So P1 plus your oil side, and then you have brine plus oil, air of 60 centimeter and mercury of 10 centimeter. So that will be equal to P2. So substituting the values here, we will get the pressure. So P1 is given as 200 kilopascal. So converting into Pascal, so multiply by 1000. Then your brine density is 0.85 specific gravity. So density will be 0.85 times density of water, which is 1000. So we get 850. So then G into 0.5. Similarly, mercury is 13.6. So we get 13,600 into G into H, mercury column height. And similarly for air your specific gravity is 10 power minus 3. So you get 1, air density of air is 1. And brine is 1.1, so 1100. So you get P2 as 196,217.3 Pascal. So which is 196.2 kilopascal. So a similar way you find it for points 2 and 3. So point 2 and 3 will be easier. So you have brine height for 10 centimeter. So P2 plus brine height for 10 centimeter. So rho of brine into G into 0.1. This will be equal to, if you write it from the other side, rho of pressure 3 plus rho of water, which is for 0.3 meters, and then for mercury, which is again for 0.3 meters. So that's what you will get it here, P2 plus brine height, pressure because of brine height, and minus your mercury height and water height, get P3. So substituting the values here, so we know the pressure at point 2, which I have calculated, which is 196.217. Substituting that and the other density values, we get pressure at 0.3 as 154,328.6 Pascal or 154.33 kilopascal. So I hope this is clear. If you have any doubts? So next question is, we have intravenous infusions usually are driven by gravity. So those are IV, which you see in hospitals. You have a glucose bottle at the top, and the IV fluids which are being passed to your blood vessels. So those flow through gravity. So infusions usually are driven by gravity by hanging the fluid bottle at sufficient height to counteract the blood pressure in the vein and to force the fluid into the body. So the higher the bottle is raised, the higher the flow rate of the fluid will be. So first, if it is observed that the fluid and the blood pressure balance each other when the bottle is 1.2 meter above the arm level, determine the gauge pressure of the blood. If the gauge pressure of the fluid at the arm level needs to be 20 kilopascal for sufficient flow rate, determine how high the blood must be placed, bottle must be placed. So take the density of the fluid to be 1020 kg per meter cube. So there are two cases. So first case, what we are saying is, if your blood pressure and the fluid pressure both are balancing when you are keeping the bottle at 1.2 meter height at the arm level, above the arm level, then what will be the pressure of the blood, the gauge pressure. So gauge pressure is nothing but your absolute pressure minus your atmospheric pressure. So that is your gauge pressure. So whatever pressure gauges you see, if you go to fill in pressure in your tire for your vehicle, so those are all gauge pressures. So it's a pressure, absolute pressure minus your atmospheric pressure. So that's the pressure which you measure when you are filling these tires and so on. So that's why you call this pressure gauges. So you need to find out the gauge pressure for the blood. That's the first question. And the second is the pressure of the fluid is given. So you need to find out how high the bottle has to be kept for the flow to happen. So we'll see how to solve this. So the first question is, first part of the question is, so we know that the fluid and blood pressure are balancing each other when the bottle is kept at 1.2 meter above arm level. So the gauge pressure is nothing but the pressure difference which will be there. So P gauge of arm is P absolute minus P atmosphere. So because both are subjected to even the bottle is subject to atmospheric pressure. So whatever atmospheric pressure plus the difference of created by the elevation, so that is the total pressure acting when it is entering the blood vessel. So this point you both pressures are balanced. So the gauge pressure here will be just the difference. So absolute pressure minus atmospheric pressure, so that will come out to be rho g h. So we know the rho of fluid is 1020 kg per meter cube, and g is 9.81 meters per second square, and height is 1.2 meters. So here we are converting it to kilopascals, so dividing by 1000. So it will give you 12 kilopascal. So that is the pressure of the blood. So if you see 12 is somewhere you would have seen, if you can see this is similar to 120 mm of Hg which you are seeing. If you measure pressure blood pressure, they give you that for top and bottom, so 120 and 80. So those are height of mercury. So similarly, to provide a gauge pressure of 20 kilopascal at the arm level, the second part of the question, the height of the surface of the IV fluid in the bottle from the arm level is again determined with the same. So instead of height, now they have given what should be the pressure be such that the flow happens. So they say indirectly they are saying that if you have to keep it at arm level, so there is no high difference. In that case, the fluid should be at 20 kilopascal pressure so that the flow happens. So that's what will be indirectly given. So that specifies what the pressure should be, the pressure difference should be. So now the same pressure difference has to be created through elevation. So your pressure difference now is again rho GH. So P gauge is 20 kilopascal divided by your density into your acceleration due to gravity. So that gives you the height at which the bottle has to be kept is 2 meters. So here at 1.2 meter your pressures are balanced, so there will be no flow of fluid inside the blood vessel. So for the flow to happen, now you have to keep it at 2 meters such that you flow, actually the IV goes inside the blood vessels. So if it is any lower, your flow rate will reduce, and at 1.2 there will be no flow because the pressures are equal. Any doubt in this question? Okay, so we'll move on to the next question. So we have a solar ponds are small artificial lakes, so which is a few meter deep, that are used to store solar energy. So the rise of heated and thus less dense water to the surface is prevented by adding salt at the pond bottom. So in a typical salt gradient solar pond, the density of water increases in the gradient zone as shown in figure. I think I forgot to add figure. Okay, so here there is nothing. You have suppose you assume a tank, so that is like a solar pond. You hypothetically assume it is a tank. So at the bottom you are adding salt to make the bottom layer of the water to be more dense. So there is a density gradient from top to bottom. The bottom is of higher density, and at the top you have a lower density. So this is done basically so that there is no circulation of water. So if you see, normally you boil water, initially there is no bubbles coming out, but even though you will see some kind of motion, you can see there is some lights, the distractions which you can see, you can observe there is kind of some movement which is there in the water. So there is rotation of water. So to avoid that and create a temperature difference, they are adding this salt and creating a gradient. So there is a less dense water, and at the bottom you have high dense water, and that gradient of the density is given by this equation. So rho is rho naught root of 1 plus tan square pi by 4 s by h. So s is your height from the top, and h is the total height of the pond. So rho naught is the density of water, s is the vertical distance measured downward from the top of the gradient zone, and h is the thickness of the gradient zone. So for h equal to 4 and rho naught is 1040 kg per meter cube and thickness of 0.8 meter from the surface zone, calculate the gauge pressure at the bottom of the gradient zone. So what will be the pressure at the bottom? So your measurement is at from 0.8 meters from the surface. So initially at the at the top there is less dense water, so that is of density rho naught. So this is for 0.8 meters. So that is your reference point. So we need to find out the pressure at that reference. So that is P1 is rho g H1. So rho is 1040 and G 9.81 and 0.8. That is 8.16 kilopascal. So again, this is we are finding out the gauge pressure here. So the gauge pressure is 8.16 kilopascal at the 0.8 meters from the surface, so which is the reference point from which you have to calculate. Then the gradient starts. So we know P is rho GH. So since your density and everything is changing, now instead of with respect to height, so if you take an infinitesimal uh, height from the surface, so you change in pressure will be dP is rho g ds. So now we have to integrate it over because your density is not constant. So we get P minus P1 at any location is 0 to S. S is your height from the surface, from the reference which you are seeing. So rho g ds. So we know rho, the equation of rho. So substituting that, we get rho naught root of 1 plus tan square pi by 4 S by H g into ds. So integrating this is what you get. So P is P1 plus rho naught g 4h by pi sin h inverse tan pi by 4 sh. So this is what you get. So then can find out at h equal to 4, and at the bottom we have to find. So s will also be 4. So this both get cancelled out. So we get tan pi by 4, and h is 4, and the g we know, rho naught we know, and P1 we have already calculated 8.16. So using that, substituting that, we will get P2 as 54 kilopascal. So that is the pressure, gauge pressure, which is acting at the bottom of the solar pond. So yeah, the only trick part was the density, which is varying. So we had to integrate it over the height. So any question in this? Okay, I think this was my last problem for today. So today was mostly on finding pressures and so on. So next week we'll focus more on finding out work for systems and process, the heat transfer and work transfer and so on. If you have any other doubts, you can ask, and I have finished what I have prepared for today. So I'm open to answer any doubts or questions which you have, or any concepts you didn't understand for this week.
Sir, can you explain how to find pressure, gauge pressure,
Gauge pressure.
the formula?
Yeah, I'll
I
go
mean the
back to this.
formula and how it is derived.
See, the gauge pressure is your absolute pressure. So minus atmospheric pressure. So what is just the difference between your pressure, what pressure which has to be measured, minus the atmospheric pressure. So that difference is your gauge pressure. How much higher or lower, how much higher compared to your atmospheric pressure. So that is your gauge pressure. And if you are in negative pressure, so compared to that is your vacuum, whatever you say. So the reference is your atmospheric pressure. The actual pressure minus your atmospheric pressure gives you gauge pressure. It's just that instead of your datum being 0, now you have moved it to atmospheric pressure. Just that's the difference between your absolute and gauge. Is it clear?
Yes, sir.
It's just a point of reference, that's it. Any other doubts? If not, we can end the session and can we meet next week. If you have any feedback on this thing, how to be improved, I'll take those also. I'll try to improve on those for the next week.
So there is a question in assignment where
Yeah,
it
assignments, I cannot help on
says that
assignments. I can help you on any doubts on concepts or those assignment problems. I cannot help you. So that's for your evaluation. So if you have any doubts, I can answer those. Okay, then see you. If there is no other doubts, see you next week. Thank you for attending. We'll see you next week, Tuesday at 6. Thank you.
Sir, just go to the last question.
Uh, Question you want? Do you have any doubts in there?
No, sir.
Okay. If you have any doubts, we can ask, or else we can end the session. Okay, then I'll close the session. Thank you for joining. See you next week.